Hello, this is lecture 3, error analysis. So the lecture notes are available in Blackboard. You have to read it. You need to know everything in the lecture notes. And for more knowledge, I suggest reading the textbook. So let me start by introducing errors. So we have three. We will talk about three types of errors. So one is approximation errors. The other one is truncation errors. And the third one is round off errors. I'm going to give one example for each of these type of errors. For approximation error, I'm going to introduce an example of approximation error based on the velocity estimation that's coming from lecture 1 and from a little bit lecture 2. We were computing the velocity of a balloon that was dropping on gravity, and then we were computing the velocity using a numerical approximation method, like the vk plus 1, vi plus 1 is vi plus some, the formula that we used. Now we will see that, also a little bit was alluded from the homework, first homework, that the true velocity versus the velocity that we computed. True velocity is the velocity that comes from the analytical solution. So analytical solution is the true value, and then we see the difference. So that's the example for approximation error. There can be, when you approximate something and then you make a miss error, that's approximation error. Truncation error, I will introduce truncation error using another example, how to approximate e to the power x, and based on that comes later in the lecture. And round off error, I am introducing round off error using another example later in the lecture using floating point. So the examples coming, so the example is velocity of falling object. Here the example that I'm going to use for truncation error is approximation of e to the power x, and here we will use floating point numbers. So after we introduce all of these three, that's this lecture is about, understanding about different types of errors that occur when we do computational analysis, or developing an engineering solution always involves some sort of errors. So this lecture will help to understand some of that. Before I go into these three examples, I want to introduce two types of errors. First of all, the one exact error. Exact error is true value minus approximation. So probably I should ET here. ET is true value minus the approximation. Now epsilon t, I'm setting now, epsilon t is true error divided by true value times, so that's a true error as a percentage of true value. So ET is true error. So the true percent relative error, which is epsilon t, that is a percentage of true error as a percentage of true value. So sorry, true error divided by true value. So yeah, the percentage of true error as a relative to true value is the percent relative error denoted epsilon t. Now epsilon a, approximate percent relative error, that is approximate error divided by approximation. What is the approximate value? Time 100%. So these epsilon t and epsilon a are their comparable quantities. Epsilon t is true percent relative error. Epsilon a is approximate percent relative error. Sometimes, I mean, we don't. If we know the true value, why would we approximate it? So epsilon t is like an ideal quantity that we won't always know, whereas epsilon a will be useful. We won't know the true value, and we will use epsilon a to have a sense of how good we are doing in terms of approximation. We will do an example next to illustrate this. Before that, let me also introduce specified error tolerance, epsilon s. So the approximate relative error percentage, percent relative error epsilon a, we will continue the iteration until epsilon a is less than epsilon s, where epsilon s is the specified error tolerance, and there is a value. One of the ways to define it is, if you want n significant accuracy, the computed value is correct to n significant digits, then epsilon s should be 0.5 times 10 to the power 2 minus n percentage. It's in percentage. So we will do an example. It's time for an example to illustrate all of these. So just to review, true error is true value minus approximation. True percentage relative error is true error divided by true value times 100. Approximate percentage relative error epsilon a is approximate error divided by approximation time 100, and epsilon s is something we will compare the approximate percentage relative error epsilon a to, and then to get an accuracy that is correct to n significant digits, we will do the iteration until epsilon s is 0.5 times 10 to the power 2 minus n. So let's go for an example to apply all of these. First, let us talk about the approximation error. So the figure 1 from the lecture note shows this is an example that we have been talking in lecture 1 and 2. This is the computing the velocity of a falling object, and we talked about two different approaches for this in lecture 1. The first one is analytical solution, which I'm going to highlight now. This is the analytical solution, which can be derived using the differential equation solution. So any given t, for example, if it is in this case, if t is equal to 4, all you have to do is substitute t is equal to 4 here, and you will get the value for velocity. Any t can be any value. That's the advantage of analytical solution, which is not always possible. That's why we are studying about numerical method. So the numerical solution which we derived was here. That needs to be computed iteratively. For example, first
we need to assume v0 is known, then we need to compute v2, then we can use that to compute v4, and then we can use that to compute v6, and so on.
So the actually how we, for the values given in one of the examples from the first homework, you can use the homework example to try this and you'll get the same. It is also from the textbook, this plot. So there will be a difference between the value that we computed using the approximation method and the theoretical value, which is correct for the under the assumption it is correct, it is perfect. So then the difference, this difference that we are seeing, that is the error, that is the approximation error, based on the that is the approximation error. So based on the assumption, you will see, you can try this, you can try with the numbers, you can just change the width size, you can change the step size, and for different things you will see the error will vary. So that's a function, definitely a function of the step size, time step size. But here the scope of this lecture is to just introduce this as an approximation error.
So that is one of the errors that we talk about, the approximation error.
So now next we are going to talk about truncation error. Okay, here's an example that we are going to do. All that I talked so far is in the lecture note, from the lecture note. So I'm on the lecture note right now. So we are going to do this example. We're going to do example 1, which is we are going to compute e to the power 0.5 to be specific for a certain number of digits. So the question is, the function e to the power x is approximated as that is given e to the equation 6. Compute e to the power x that is approximated to 3 significant digits. So we want to compute e to the power x that is approximate to 3 significant digit. Before that, this expression, how it came about, I'm sure you studied this in first year through Maclaurin series or something. So e to the x can be expressed as a series of this expression 1 plus x squared divided by 2 factorial, x cube, there's an error there, x cube divided by 3 factorial, and all the way to x to the power n divided by n factorial. So how many of these terms we need to use so that we will get an accurate value of e to the power x that is correct to 3 significant digits. Now we know the answer, so if I already have the answer by using a computer. I found out that e to the power 0.5 is actually 1.648721277. That is accurate to that many number of digits. That's very accurate. But here we are going to do an experiment, how this all worked out. So the question here is, how do we want to approximate e to the power x so that it is correct? So should I write e to the power 0.5? One approximation is just 1. That is the first approximation. Second approximation, e to the power 0.5 is 1 plus 0.5. That is 1.5. Just always compare that to the true value. The third approximation is e to the power 0.5 is 1 plus 0.5 plus 0.5 squared over 2. Like that it goes on. So, but we learned some theory that if it has to be, we don't want to compute too many terms. We don't want to compute like 25 terms, because that is too much. We will be doing a lot of extra computation for nothing. So it is required only for 3 significant digit. It should be accurate to 3 significant digit. And then we will use the theory that this epsilon s, we will keep on computing, and we will keep on computing the epsilon a also, and every time we will compare it to epsilon s. As long as epsilon a is greater than epsilon s, we will continue.
when it's become less than epsilon s, we will stop. So the first thing is to compute epsilon s. The theory equation 5 says epsilon s, s is specified error tolerance epsilon s is 0.5 times 10 to the power 2 minus n. So if I substitute a value here, 0.5 10 to the power 2 minus n. So we want it for 3 digits, that's why 3 there. So that is 0.5 times 10 to the minus 1, that will be 0.05 percent. So that is our epsilon s. So we have an epsilon s now. Now let's go and compute the approximation. So the first approximation, as I showed there, is e to the 0.5 is 1. Second approximation is e to the 0.5 is 1 plus 0.5, which is 1.5. Now we can compute our first epsilon a, because we have two subsequent estimates. So epsilon a is 1.5 minus 1, that is the approximate. This is the, because 1.5 is an approximation, 1 is also an approximation. So that is the approximate error. 1.5 minus 1 is an approximate error, and the present approximation is 1.5. So that is divided by 1.5. And then I should have multiplied it by 100 to get 33.3. So it is, the answer is multiplied, but I didn't show it. So I will fix that in my notes. So that is 33.33%. Is that greater than epsilon s? Yes, sure it is. Epsilon s is 0.05, so we had to do more iteration. So let's compute a third approximation. That is 1 plus 0.5 plus 0.5 squared over 2. That is 1.625. And let's compute the epsilon a. 1.625 minus previous estimation 1.5 divided by this, once again, times 100. I will put it in the lecture note. So that comes to 7.69%. Still, that is greater than 0.05. So the remaining, we have to just keep on continuing. So that is what I did, and it is shown here. So first, the epsilon a was 33.33, then the second one is 7.69. Okay, here, this is one you have to look at it. 33.33, we know how we got it, and 7.69, and the third point is 1.27, and the fourth one is 0.158, and the sixth iteration, is 0.01. That is 0.01 is less than the epsilon as. So that is less than epsilon s, which is 0.05. So this is the number that we got. That is correct to 3 significant digits. Let me write this below this: 1.64869697166. So it is good up to 3 significant digits. If you approximate it, there's no way these three will be different. So that is how we end up, because the next 8 might, if you approximate, that might change, but if you, for whatever the approximation you do, the 3 significant digits will be always same. So that is how we use the theory that we learned so far to compute e to the power x that is accurate, not e to the power x, to be specific. We computed e to the power 0.5, and now we can confidently say this number that we computed, which is right here, we can confidently say this is accurate for 3 significant digits.
Example 7. Here we are going to see how how this number representation works. So let's take a look at the floating point number system here. So the sign of the number is allocated for 1 bit. 1 bit is allocated for sign of exponent. It can be more bits. And then magnitude of the exponent allocated 2 bits, and then magnitude of Mensa 3 bits. Now the values, the sign of the number 0. Now we have to tell, we have to kind of define it. So we are defining it. 0 means positive, 1 means negative. So that is for the sign of the number. Same for the sign of the exponent. 0 means positive, 1 means negative. Now with this, the magnitude, what are the possible magnitudes we will have? Possible values for the magnitude. So magnitude is a 2-bit number. So how many different values we can make out of a 2-bit number? So 4, 0, 0, 0, 1, 1, 0, 1, 1. That is all the possible numbers that we can make out of a 2-bit number. So this is 0, that is 1, that is 2, and that is 3. Well, you can use this approach right there to find that. Now, since there is 0, we can make 7 possible values, because 0 is considered positive. So, and then there cannot be a negative 0. So that is gone, because we have when it is positive, we can use all 4 values. When it is negative, we will only use 3 values: 0, 1, which is 1, 1, 0, which is 2, and 1, 1, which is 3. So negative 3, negative 2, negative 1, 0, 1, 2, 3. These are the possible exponents. So we have seen what is the possibilities for sign. It can be positive or negative sign of the number. And then we have seen the possible values for the sign of the exponent. And we have seen the possible values for the magnitude of the magnitude and sign together. Here, this whole thing is the sign of the exponent as well as the magnitude. Both are considered in this table. Now, possible values for the Mensa. So we have three bits here, and this table tells what are the possible values for Mensa. So we have, if you have a 3-bit number, there are 8 possible values. So here we have 1, 2, 3, 4, 5, 6, 7, 8. So these are the possible values for Mensa, and then that is written in base 10 as shown here in this table. Now, if you think about the decimal number, for example, let's say 88.645, what we have here, this is 10 to the power minus 1 times 6, this is 10 to the power minus 2 times 6, and this is 10 to the power minus 3 times 6. And exactly the same way we will treat the Mensa. Why? If you want to know why, you should refer the book. I'm going to skip that. But these three digits, this is 2 to the power minus 1 times whatever the number we have. This is 2 to the power minus 2 times whatever the number we have. And this is 2 to the power minus 3 times whatever the number we have. So that is how it will be. That is how it is defined. Just think about this as an example. When you write a floating point number, you will in decimal, you will always write 1 point or some 748 times 10 to the power 6. If you have limited space, a big number, that is how we will always write. Here we will have some number. We don't write 12 times. Sorry, we don't write 17.48 times 10 to the power 5. We don't write that. We always write 1.748. So we are following the similar notation, similar tradition in the binary. So the Mensa is treated this way.
Now with this understanding, let's write the smallest possible number that I have sufficiently introduced this floating point number system. So let's introduce the smallest possible number that we can write. Sorry. So what is the smallest number out of these? You know, if you just look at this, 2 to the minus 1, 2 to the minus 1 plus 2 to the minus 2 plus 2 to the minus 3. So when you add something, it is, it increases value. I'm talking about absolute value. So the smallest value is this, 2 to the minus 1. So smallest Mantis is 2 to the minus 1. And what about the smallest exponent? Smallest exponent is minus 3. So we'll just use this formula, Mantis time base to the power exponent, smallest Mantis time smallest base to the power smallest exponent will give us the smallest number. The smallest Mantis is 2 to the minus 1, base is always 2, and then 2 to the minus 3 is the smallest exponent. That gives us, so 0.0625 is the smallest number that we can write, smallest positive number. If it is smallest negative, you have to consider that side. So what about the largest number? So for largest number, what is the largest exponent? If you look at all the exponents we have here, the largest exponent is 3. And then what about the largest base, Manisa? That will be 2 to the minus 1 plus 2 to the minus 2 plus 2 to the minus 3. So if you combine that, m times b to the power e, that is the largest number. So the largest number that we can write is 7. Now there's an example you should try. That's also a homework, so I'm not really worried about that example because you're going to do it as a homework. Write down all the possible. The number is going to be quite large, but give it a shot because for homework, what I did. So these 3 questions, question 1 here, and question 2 and question 3 are homework. Basically, I'm asking you to write all the possible number, but I just reduced the 1 bit so that you won't go and get that many. Basically, you had to basically fill this table. I already gave some numbers there to help you out. So that's a homework, and then there are some other questions. Just read them and do it. So the summary of this lecture today is we talked about errors. We talked about 3 types of error. Approximation error. Approximation error you can understand based on this velocity computation. How we used numerical method to compute velocity, and also we can use if you know the true velocity, which we happen to know in this toy example. The other is truncation error. We used e to the power x, how we compute e to the power x as an approximation, we saw that. And then finally, for round of error, we took this floating point number as an example. The goal is to make you aware of different types of error, which is always case in engineering. Whenever you design something in engineering, there will be errors. So I hope this lesson gave you some exposure to that. But I would suggest reading the corresponding chapter in the textbook to get more in depth and to get more to be exposed to more examples. There are problems in the book, so you should try all of that to get a wider knowledge. Thank you so much. So